Well, thank you so much. And thanks for coming out on a sunny evening. So it's a commitment to come to a talk while you actually want to enjoy a dinner. So we hopefully make it not too painful. So I'll talk about quite a common thing, I think, in pretty much all areas of sciences. We see sort of machine learning AI sort of coming in, bursting into fields, and it makes massive differences in many, many areas. And as I'll show you in a minute, it made a massive change in weather forecasting. It changed the field entirely in a very short time. But will it do the same for climate? And that's something we have to think about. I put a little protest against the renaming of Dining with Dinosaurs in here, but anyway, we still like it. Good. So I was asked to say a few words about myself before, so I'll try to keep that brief. So I started to get really into climate and climate change and quite angry about it as a teenager. So I thought, what can you do about it that's a bit better than just being angry and a Greenpeace member? So basically became a student of atmospheric physics. And then in Germany, that sort of family and friends and so on basically predicted I would be either a taxi driver or in Germans, they use basically this word Wetterfrosch, a weather frog. It's a frog that predicts the weather by climbing up and down a ladder in a glass. And basically I was just called sort of weather frog. So that was my destination. But then I chose to not stay in the glass. And so went to Reading, did a master's there, and then went back to Germany for a PhD and stuck sort of to the climate area, went more and more into climate from there. And then as many of us sort of did a dip in the US and was at Caltech for a little bit. And then I came back to Oxford and sort of have been here since almost 20 years. So I begin to understand the system a little bit. And then I do a little bit more from the basic physics. We went more into AI stuff, and Annie nicely introduced already sort of what we do here in Oxford and some of this. So that was just about me. But in Oxford here, I'm super privileged to work with a fantastic bunch of people. And that's sort of our research group. And what I love about this group is we come from all different backgrounds. So we're physicists, we're mathematicians, we're computer scientists. And so we study one thing, and that's clouds, as you might have gathered by all the pictures already. But we come at it from very different angles and pretty much from all around the world. So it's a real joy. And pretty much everyone in the group is smarter than me, which is extremely helpful. It's quite cold today. We probably knew that a while ago. Oh? Did you trust the weather forecast for today? A little bit? Do you trust the weather forecast in general? Most people say no, or not so much. I mean, it's actually quite a remarkable field because weather forecasting, even though everyone complains about it all the time, it's had sort of what people call, and named it and also in a paper, the silent revolution. So what this shows us from the leading weather forecasting center, basically the increase in forecasting skill. This is one metric. You can find many metrics. Obviously, you choose your favorite metric. But basically, it shows sort of from sort of the 80s to mid sort of 2010s, how the forecasting skills for different lead times of the forecast increased. And you basically see what was possible maybe in the 80s, where you could do a 3-day forecast, we now can do with the same skill, a 5-day and so on. And it's basically just creeping up. And for a 3-day forecast these days, it's near perfect. It's extremely good, even though it's quite a complicated system in many aspects. And so this has gone a little bit unnoticed because everyone, if it rains on you, you tend to remember quite a bit. But weather forecasting has improved massively. So the basis of these models, traditionally, and don't worry about the equations. Not everyone here is a big fan of equations, and that's absolutely nothing to worry about. The basis of these traditional weather forecasting models is basically we take the Earth, we want to simulate the evolution of the atmosphere, so we discretize it in some way, so we basically make a fine mesh around the Earth, and we solve a set of equations that we know, which is actually a whole book full of equations with just numerical methods, and we predict basically the evolution of the atmosphere. And traditionally, the problem with that has been, and still is, that the Earth is quite big. And computers are not just big enough yet. So a traditional climate model, this grid spacing is on the order of 120 to 100 kilometers. Now, when you care about things like clouds, and I'll tell you soon why you should care about clouds, many processes happen on scales of hundreds of meters, kilometers, and so on. That means basically these models solve the equations explicitly for the larger scales, but then the small things, and in particular clouds, are what we call parameterized. So you have some statistical estimation what the clouds would do in dependence of the large-scale variables. And this introduces quite a bit of uncertainty. So now, one way out of this, and that's one direction we're doing, and many people do, and we're very excited because computers get bigger and bigger. We can brute force us out of this to some degree. So we take the biggest supercomputers in the world, and we build very numerically efficient models, and we basically solve this problem just by brute force compute. And that means sort of if you had a traditional climate model with a resolution that I just mentioned on the order of 100 kilometers, this is what clouds would look like here. And if you think you want to predict floods in a small catchment area of a river over Africa here, you obviously don't have a lot of trust in these, in traditional climate models. But nowadays, when we push this, and we push this quite heavily in a big European project, NextGEMS, we basically then really resolve clouds here at a scale of 1 kilometer. The Japanese always have the biggest computer, they're at 300 meters. So it's basically, you can see it just scales with a computer. But this has a lot of promise in absolutely changing how we do weather prediction and climate prediction already. But it comes at this extreme high computational cost. And as a research group, actually a single year you run on this on a climate model costs you probably 30,000 pounds or so. So it's quite expensive. But also it doesn't allow us to do everything we want. So it's quite natural to think about where does the AI come in and could it help us overcome some of it? So lots of us have been thinking about this for a long time. So actually in 2018 or 2019, we held an expert workshop here in Oxford. And this was pretty much all the leading groups in the world there. And they're still basically leading a lot of the science around the world. And we sort of discussed sort of, will AI, how much will it do for weather forecasting and climate forecasting and so on? And then conclusions were written and published. And when you look into the details of the conclusion, effectively it says it's currently difficult to envisage that this AI will basically replace numerical models on medium-range timescales. That was in 2019. That is not a long time ago. And it's understandable because this, again, is sort of a skill versus timeline plot here. And this were the first dabbles and attempts in 2019 of some of the people at this workshop to do something like weather forecasting with a machine learning-based model. And this, in comparison, was the best reference physical model that solves this whole set of equations that we said before. And you see the gap is massive. So in 2019, there was absolutely no skill, basically. But then you see this rapidly increasing curve here. And particularly interesting is this guy. He did it as a summer project. He just decided this must be an interesting project, and he introduced some of the approaches that are now in the leading models, and did it almost alone, and then later on things like Google and others jumped on this. So it's really all these models that came in here, they're all sort of purely data-driven models. And they work in various ways, and at a dinner like this, we won't go in all the details, but quite often you take sort of the input, the weather state, you encode it somehow into some latent representation in a sort of compact space, you process in time, you basically make a forecast, and then you decode it again to give you a map of the weather. And that is usually successful. This was here the graphs from the Google DeepMind team. But what's often overseen here is that actually these models are so successful because traditionally they just trained on the physics-based models. They took a physics-based model and learned from the physics-based model how to do weather forecast. And interestingly, they trained so well and had so much input that they actually outperformed the model they trained on, which is an interesting concept to think about. But basically, these models rely on these physical models as training data. There are other approaches I won't touch too much about where people get around this now. But this has been a real revolution. So now, in physical climate modeling space, it's effectively we use a weather forecasting model. Yeah, climate is just a longer-term average of weather, and we just run it for longer. So you can think that if we now have also good AI weather models, can we just run them longer to make good climate prediction? And that's sort of the question a bit I ask in this talk. And I want to put in some caveats here. It may not be just as easy as some people sell it. And I want to focus on some of the key uncertainties. And you might have come across my obsession of clouds already, but I'll talk a lot about clouds. So one of the key uncertainties here are clouds. You see clouds from space, so this is the Earth seen from space. You see the individual passes of a satellite sort of going by, and you basically see every time I'd observe the Earth. And clouds cover about 70% of the Earth at any given time. So it's a lot of clouds, and the fact that you see them tells you they reflect sunlight back to space. And the net effect they have is about a number minus 20 watts per square meter. May not mean anything to you, but I can tell you this is about 10 times larger effect than the anthropogenic effect of CO2. So if you change clouds by 10%, you can totally double or offset global warming from anthropogenic emissions. So it's really important to understand how clouds change in the changing climate. And well, the question is, how would clouds change? And the difficulty often is we look at the Earth, we have a lot of satellite observations, but it doesn't directly tell you how clouds would look like if they were unperturbed. But sometimes we use analogs. And one of these analogs I'll explain a bit more detail. We just look a little bit more careful in this corner of the south of the Northeast Pacific. Well, still don't see much that looks like a cloud perturbation. But if you go a little bit further, we can discover in these cloud decks these interesting stripes, near linear feature. And you don't need to look around a lot to find these. Anyone wants to guess what these near linear tracks are or features in these clouds? They're not natural. Yeah? It could be planes. These clouds are very low. It's not contrails. Most people think it's planes, but it's actually the tracks of ships. So why would a ship make a bright stripe in a cloud? A ship emits small particles, aerosols, and every cloud droplet in the atmosphere forms on one of these small particles. So in the area of the ship track, you have more and smaller particles, and you form more cloud droplets. With the same amount of water, you have smaller droplets, and they are brighter. So these ship tracks provide us this sort of opportunistic lab. We can test how air pollution in general affects clouds. And so we can exploit this to then constrain the effect of air pollution on clouds and climate. So just to give you a hint, so this is sort of the total global warming we would expect from anthropogenic CO2. And this is the actual warming, and basically about half a degree of warming we currently offset by having air pollution making clouds brighter. So we're masking a lot of the warming by air pollution. It's great, so we can pollute more and keep the Earth cooler, which is true. The problem is air pollution kills about 6 million people a year. So it's probably not a good incentive to keep doing that, but at the moment it helps us half a degree. And this plot is outdated. By now we would be almost at 2 degrees if we were to remove the air pollution. So one way to study this, just to give you a little bit hint, what we do then in climate science often with machine learning, in this case, we use just standard computer vision methods, fairly out-of-the-shelf methods, and we just basically have a training data set where someone else abused PhD students to label these ship tracks, and then we take this training data set to train a simple, fairly standard UNet to basically detect these tracks. And then we can deploy this across a whole satellite record of 20 years. So this is several petabytes of data, I think on the order of 20 petabytes of data that we crunched. And then we can find basically these ship tracks globally. And we can see that they're nicely aligned with the shipping routes, which you see in these dashed lines, which we know from the emissions of ships. And we can use it even to detect changes in emission regulation. So you see here the same map as before, but this is before and after 2020. And in 2020, the IMO, the International Maritime Organization, reduced the pollution from shipping substantially. And we can see this. So the ship tracks really started to disappear. So it's just a nice little example of how sometimes out-of-the-shelf basic machine learning techniques that don't get anyone excited anymore as such as a method can be used to really change some of the studies we can do in environmental sciences. The other way we can change clouds, and that is a little bit more subtle and I can't go in all the mechanisms, is by feedbacks. So feedback is basically or a climate feedback would be that the changing climate, in this case, affects the climate system, which again has a radiative effect that affects climate. So the one that everyone sort of knows about and has heard is the albedo feedback. That would be in a warmer climate, you would have less ice, you would have less snow and ice, you would have less reflectance by snow and ice, and thereby the Earth's albedo gets darker, basically, and we absorb more sunlight, and the warming accelerates. So that's a very commonly known feedback. It turns out also clouds change in a changing climate, and these are results from two sort of sets of climate model intercomparisons. And you see CMIP6, the later one is, so this is the latest intercomparison. Each little ring is an individual model. And you see here basically the additional radiative effect you get from every degree of warming. And you see, on average, these models think clouds have a positive feedback. So as the Earth gets warmer, clouds albedo reduces and it will accelerate warming. But you can also see the models don't agree at all. Some model thinks there's nothing happening, some thinks it's actually cooling, and some of them think it's very strongly. So actually you can track this back to being then the biggest uncertainty in our ability to predict how warm it will get in a future world. And that's why a lot of people are interested in these cloud feedbacks. So, and that raises then the question, if we now go to purely data-driven climate modeling, or if we were to go this, can we generalize from present-day observations to future states? Some of these feedbacks may not have occurred yet. If you train on data that was before the ice packs melted, then you wouldn't be able for your model to learn these changing effects. And in particular, for climate feedbacks related to clouds, is also we don't know which of these feedbacks will trigger in the future. And thereby these additional feedbacks are just really uncertain. So how bad is it? So this is the first attempt. This is hot off the press. It's actually something that's not even published, and I'm barely allowed to show it, I guess. But it's the first intercomparison where people got together and compare the first attempt of machine learning-based climate models. And this is just the base state compared in these models, where we just look at the biases at sort of the temperature at a certain height in the atmosphere and just see how different these models are. And some of these, this is sort of the Google model, there's the NVIDIA model, and you see actually what I didn't talk about much. Interestingly, there's a lot of commercial players in this space. Many of them claim they will solve that problem very quickly. And that's not clear at all yet. But you see basically there's a lot of different models, and some of them are smaller academic groups. But most of them have some private funding in one way or the other. I think the main take-home message from this plot, it looks a bit like a mess. Yeah, so these are different months. And you see basically the biases these models have are absolutely not coherent. They're quite large. They're several degrees. And they don't really make entire sense. But they're also not entirely out of range. So also traditional climate models might have biases of this magnitude. What's a bit more worrying is a simple test you give climate models initially, them with all things like changing CO2 and all the emissions and so on. But a very simple test in this idealized setup would be, let's just make the sea surface temperatures a little bit warmer and see how models respond. And physically, climate models have a fairly coherent response normally to that. These models, not so much yet. So this is basically the change in effectively surface temperature or surface air temperature to when you warm the oceans by 2 degrees here or by 4 degrees. You see some of these models give you really strong, well, some of these models give you globally uniform warming, roughly of the order of the perturbation. Some of them give you extremely strong apparent feedbacks that drive extreme warming in the higher latitudes, so quite often that would be related to ice or clouds typically. And some of the models give you something that's you can't explain physically at all. So these models are obviously pushed out of their training distribution, and they must really struggle quite a bit. There's no physical mechanism at the moment that you can think of that if you warm the oceans by 2 degrees, the land surface gets colder by 4 degrees. So these models are just struggling. And that's the current state of the art. In defense of all of these groups and all the many colleagues that are working in this, these models started to be built only 2 or 3 years ago. So physical climate models, we had a 50-year history of building these models. This is very fresh. But still, when people say this, we will solve this problem in a year or two, it's probably unlikely to happen. In my view, but that's a slightly biased view, but in my view, without having generalizable representation of clouds that we can feed into these models, one way or the others, these models won't succeed. Because we know, as I've shown you, in traditional physical climate models, it's the cloud feedbacks that drive the biggest uncertainty among predictions. At the moment, some of these models have no explicit representation of clouds at all. They don't need to. You can bypass this in a machine learning model. They just learn some of these effects. But I think without constraining this problem, we will not make any progress. So that's why we're working quite a bit in that space. So one thing we're playing with is a paper that's actually just being submitted in a couple of days. But we're basically working on, some of you will have heard these buzzwords, foundation models. This is it's basically a machine learning model you train with a lot of rich, diverse set of multimodal observations. And here, again, some of you will be quite familiar with the method, some of you don't, but that doesn't really matter. So we're working on a model that's meant to learn the full control of clouds by their environment. So when you have a certain atmospheric state, we want to predict exactly this is what the cloud should look like in a probabilistic sense. And we use this model that's a flow matching model, so we predict sort of a deterministic velocity field that from a random distribution initially sort of learns how to transform this random distribution to sort of your target distribution. And for those of you who know this, we condition here on the atmospheric state. So we say we feed it the state of the atmosphere, and it should learn for this state of the atmosphere, the cloud should look like this, but certainly not like this, because the velocity field brings us in this space. So this is something we're working on. We've trained on quite a lot of satellite data, and we're actually quite excited. It works quite well. So here we feed it an initial atmospheric state, and this would be the corresponding satellite image. And it basically generates probabilistically many different types of samples. So it's, for those of you who don't think so much about sort of conditional modeling, this is the equivalent of your text-to-image generator. When you say, you basically, I want a dinosaur in Rubin College with some people having a dinner or so, and you get a nice image of that. Here, your text that you provide to the image generator, we replace basically by the atmospheric state. And we basically embed this in a different way. Yeah? But it creates really quite realistic images. We go in a lot of evaluation, but the cool thing is it doesn't just create images, but we can also create things like cloud top height. We can learn basically from the satellite data the vertical distribution. We can learn how much cloud water is in there. And a trained observer would tell you probably this looks very much like an ice cloud. And actually, indeed, the model has also learned that this is a high cloud and primarily an ice cloud. So we think this is really one way of how we ultimately understand the control of clouds for climate. But this is obviously, at the moment, you can say it's just images, so it's a little bit limiting. So the next steps for us is to throw a much more rich set of observations against this. In particular, we're really keen to constrain the vertical structure. Cool new satellite data. And I show you results here from a project. Some of you might have heard of FDL, the Frontier Development Lab project. It's sort of a public-private partnership between ESA and NASA that moderates these. So they allow people, and you can apply. Actually, let's open the call. They allow to work in a small group of 8. One project. In this case, it was 3D cloud reconstruction. Half of them tend to be sort of machine learning DPhil student or PhD students. Half of them are more domain experts, and you get unlimited credit and so on for cloud, and you actually get paid for it. So it's quite good to do. And in this project, this team where some of our group members were involved, they basically took geostationary satellite data, which is a satellite that hovers about above the Earth, so you get the temporal evolution of clouds as well. And they used this to train a model like this to predict cloud structures, but then also fine-tuned this model then with CloudSat. And CloudSat is a cool satellite. It's the first cloud radar in space. So it's a radar that scans the vertical structure of clouds. And so when you combine this, you don't only have the image, but you also have the vertical structure. And just to show you one cool animation they created from that is basically Here they applied the model that they trained then to predict Hurricane Dorian, and you see the image here in the back. They learn with the model, basically the radar reflectivity, projected basically again on the surface, but you also see here this real model size through the storm, the model learns. There's obviously uncertainty about this because the information content is slightly limited, but it's actually quite remarkable when you look at it in more detail how well these models predict the vertical structure of clouds, even though from the image alone you wouldn't expect it to do so. So it very much learns the physics, how the cloud vertical structure depends on the evolution of the cloud top properties in time and space. So I think this is a super exciting time to do this kind of work because we have the data. We have ideas how we want to do it, and we now have to do it. So that's what we're sort of as a group working on. So we want to, I think I can retire once I've done bullet point 1. So once we fully understand the control of clouds by the environment, which means basically you learn the perfect mapping between the atmospheric structure. And what I mean by structure is typically vertical fields of temperature, humidity, and wind. That's pretty much explaining everything you need. And then how this links to the cloud morphology, the structure of these fields, and you see they can be super complex. And then the associated climate effects. And if we have a complete model that describes this, we can build small models from this to replace all the climate model parameterizations and so on, as long as it generalizes to different climate states. So this would be great. If we get it done, we just need a large chunk of money. So this leads me also then to the end of the talk. Will AI or machine learning really transform climate prediction? I personally think yes. If you ask many of my colleagues, they say no. Primarily in physics, we still have a very strong grounding in physics, and we don't think it should replace the physical thinking. But I think ultimately, these methods at the moment seem to allow us to exploit a lot of the information content that we just throw away, typically in observations at the moment. And so it's quite exciting. But I think it's a long way to go, and it will take us quite some time, and it won't be done in the 2 or 3 years that we needed for weather forecasting, unfortunately. Okay, with that, I think I'm finished. And I think we take questions afterwards. Is that right? Or do we take now?